2, 1. This will be a long one. Probably the hardest sketching example that you'll find on YouTube or anywhere. So this is intended for any student who's kind of going through and has gone through functions and then wants to apply some of their calculus to accurately sketch an actual function. Now this is a piecewise function, so you'll notice that it's defined on the left of 2 in one way, and then on the right of x is equal to 2 in another way. And both of these are not the easiest ones because they're rational, so we have to worry about numerous aspects. Let's get started, okay, on this kind of to try to see if we can sketch it one by one. So here are the steps that I follow. I typically will go first to try to find out what the domain of my function is. Now I have 2 items in here. So for this number 1 item, if you take a look at this, we obviously have a problem because we have at x is equal to -3, okay, this is going to be either undefined or indeterminate. Now, it doesn't matter if it's undefined or indeterminate. As soon as you find out that you have a 0 in the denominator, you know that the function's not defined there. So that's going to be one problem that we have. Now, that, okay, is going to lead us to the second function. So the function which is to the right of x is equal to 2. So we're going to do that one as well. So let me just kind of write in here. So definitely x cannot be equal to -3. So that's from the first one. From the second one, we do again have a problem because we have a denominator. Now let's take a look where this function might possibly be equal to 0. Maybe it's not. I don't know. So I'm going to take the denominator and we're going to set it to 0 and try to figure it out. So for that second component, so I'm going to paste this in here. So what we're going to do is we're going to set this to 0 to see if we have any, undefined or indeterminate problems with this one. So for this, I don't know if this is, oh, actually, hold on a second. So this is x minus 5, x minus 6. So this is just factoring of a quadratic. If you forget, use the quadratic formula, right? If it doesn't pop up at you, just use the quadratic formula just to check, where possibly you might have some roots. So it looks like, again, we will have problems at x is equal to 5 and at x is equal to 6. So we cannot have it here. Now let me go back in here. I'm going to just take this function, okay, and highlight it for you. So you can see that there's x minus 5 in the numerator. So it definitely will cancel. So let me just kind of copy this down and then paste it in here. So, if we would substitute, and I would take this thing out of here, delete, and then just, okay, this is the factored form. So duplicate it, put it at the bottom. So we will run in and see that this is going to cancel this off. However, regardless, this function's still not defined at x is equal to 5. So this is going to lead to having a hole at x is equal to 5, sorry, and that's going to be one of the steps that we will have there. I think it's step number 3, find any holes. Well, there you go. We've just found a hole right there, but we'll come back to it. In any case, so this will turn out that the domain for this will be that x is going to be defined pretty much everywhere, except x is not going to be allowed to be -3, 5, or 6. That's going to give us some headaches there. Now at x is equal to 5, we have a hole, so that will definitely highlight something for us. But at x is equal to -3 and 6, it looks like we're going to have vertical asymptotes. Okay, so now we have our domain. Great. So now the next item is indeed, so vertical and horizontal asymptotes, or any asymptotes that we have. So let's take a look at this. So find vertical and horizontal asymptotes. So for the first one, we do have, so this and this thing, we have a vertical asymptote wherever the x is not defined. So for rational functions, if you don't have it defined, so in this case at -3, it's going to be a vertical asymptote. So I'm going to have a vertical asymptote there. And let me just start sketching this out in here. All right, I just wanted to sketch this out already. Okay, so we have a vertical asymptote at -3, again, because of it's a rational function. And then for the second one, so for this one, we do have another vertical asymptote that's going to be at x is equal to 6. All right, so I can draw this one in here as well. So here are our vertical asymptotes. Now, horizontal asymptotes, we typically check when we are trying to have x is approaching to positive infinity and then x is approaching negative infinity, to try to see if it actually slants over or goes up to, you know, some kind of a horizontal asymptote at some point. So, you know, we have 2 split in here. So, sorry, split at 2, right? So to the left we have one function, to the right we have another function. Okay, so, you know, we can find out. So on the, as x is approaching to positive infinity, let's take a look and see what happens there. So that's really the function for x, which is, you know, greater or equal to 2. I removed just that hole. We'll worry about the hole afterwards. So within here, so if you let x tend towards positive infinity, so what's going to happen, and this is a neat exercise for yourself, so what you really have is you have x squared all over x minus 6, right, minus 8x over x minus 6 plus 17 over x minus 6. And what you notice is that, well, as x is approaching to positive infinity, so this basically goes to 0. As x is approaching positive infinity, so this whole thing basically tends towards 8, right? So that will cancel. And so, or 8 or minus 8, I apologize because of this. And then as x is approaching positive infinity, so again, so this is going to be really tending towards that. So it looks like we don't have a horizontal asymptote, but it looks like we have a slant. So x minus 8. So as x gets bigger and bigger and bigger, it basically approaches a linear function. Just, you know, your y is equal to x minus 8. So it looks like that is a slant asymptote that we're going to have, you know, somewhere further out. So, you know, we're going to be being careful with that. Okay, so this is some kind of a slant. Now, what about for the other one? So that is this right here. So let me take this and copy. Let me bring it down. So what about for this one? This is for x is less than 2. And as x is approaching to negative infinity, so again, you play the same game. You basically will say, all right, so x squared, x plus 8, plus 4x, x plus 3, minus 5, x plus 3. Well, as this is approaching negative infinity, so what happens to this? It just gets smaller and smaller. This basically tends towards 0. As this approaches negative infinity, so notice the x and the x will cancel over there. Doesn't matter if they're negative, because negative over negative, so that's gone. So this is going to be approaching 4. And then this right here, well, you know, so you have one of the x's. Okay, so here's the other x. So this is going to be approaching basically kind of x right here. And as x is approaching negative infinity, so this is going to be tending towards negative infinity. So it looks like we have another slant, all right? So it's going to be approaching this particular line, but it's going to go on the negative side, all right? So on the left-hand side here, so this thing's going to blow up and it's going to go negative, all right? So that's what's going to happen over there. So we do have vertical asymptotes. We don't have horizontal asymptotes, but we seem to have a slant And this is a nice way of trying to see what happens to our function as, you know, kind of on the extremes, positive and negative infinities. Okay, so that's number 2. Number 3, well, number 3 we already solved, so we know what the whole is. So that happens at x is equal to 5. Now, what is that value? Okay, fine. So we know what's that value. So that's this thing. So let me copy this. So we can substitute it into here and find out what that exactly is. So let me be right back. All right, so we have it basically at 5. So it looks like it's -2, so it's on the negative side there. That's what you have right there. So we have 1 whole. That means the function just won't be defined there. All that happens is the function basically will look like this, except only at 1 point you have a hole. That's why we call them a hole. Put up a link up above there for holes if you want to go over that concept again. So that's number 3. So let's see, what else do we have here? So number 4, find the x-axis crossings. Okay, well, the x-axis crossings are annoying. So let's take a look. So on our function, you know, so we need the crossings here. So copy. So I need to find the zeros of this. This is going to be number 4. Let's paste it. So I have to set this equal to 0 to see what the roots are. So this is irrelevant for us in terms of crossings. Does this factor out? X minus 5, 4, plus 5, x minus 1. Okay, so it's actually, you can factor this out, so that's not bad. That's just being comfortable with quadratics. So that means I have 2, so x is equal to -5 and at 1. So those are my 2 crossings on the left hand side, -5 and 1. Let's put that in there, -5 and 1. So right here, okay, that's on that. Now the other one, so that's this one right here. Copy. I don't even know if this has any crossings, but we'll find out. Again, you know, if you're setting it to 0, the denominator is irrelevant. Okay, this one I can't see. I'm just going to use the quadratic formula to see if this has any roots. Okay, so this is not going to have any roots at all, because that square root, you're going to get -4 underneath there. So that's not possible. So that means this actually doesn't have any zeros. So those are the only zeros we are going to be running into. So there's going to be just 2 crossings in here. And I guess the rest is going to happen around those asymptotes. Okay, so we have our 0 crossings. Now the next item that I like to do is create test points. So create test points to identify where function is positive or negative. Now the way that you do that, you basically, so you know, the way that I do it is once you sketch this out, you're just going to go one by one in terms of the test. So what happens on here, right, on the left hand side? So is the function positive or negative? Now we actually already know that it's negative because of the fact that I was doing this test right here. So what happens, you know, as x is tending towards -infinity? So we said it slants towards this, and because it's negative, so it's going to be a negative number. So this, our function is actually negative here. Now, if you are not doing that, so like if you are in a class and they don't really ask you to find out what happens as x is tending towards infinity and -infinity, then in those situations you can just, you know, take in -6, so take a test point or test value on the left of -5 and then substitute it back into your function and see if it's positive or negative. So that means here the function is actually going to be negative in here. Okay, now what about, so now next, okay, so what we do is now we take a test point over here. So I'm going to take -4 and substitute it back in and then check what that gives me. Okay, so I'll be right back. All right, so it's positive there. Okay, so we already kind of have a pretty decent idea on how this is going to start to look like. But I'm just going to leave that. So negative and positive at the moment. So now the next item that I'll do, so I'll shift over between here and here and find out, so what happens on this interval? Where is this function? Is it positive or negative? Now, a nice test point, well, in this case, because it's 0 is included, just take 0. And in fact, if we find 0, we're going to knock off the next item. So notice it says find y-axis crossing there. So you see that over here. So that means, we can take one stone and get rid of 2 birds here. So I'm going to just take 0 and find out what that gives me. So hold on. Okay, so it looks like it's negative. All right, and it's about negative 1.6666, so approximately 1.7. So we know it's going to be crossing the y through there, and it is on the negative side. So again, if it is negative, so that means it definitely is going to be blowing up in this direction. All right, so we have that. Okay, within here, actually on the left, as it's positive, so this is definitely going to go in this direction. Okay. Almost just crosses through -5 and then continues on the slant. So we kind of know what's happening there just by doing our test points. Now let's, kind of continue in here. So I guess what we can do next, we're supposed to find this region right here. Now it's actually stops at 2. I'm going to just substitute 2. I know that it's not defined at 2 on the left-hand side, but it does actually let me know if it's above or below. So what happens to the functions now? So let me just substitute 2 in here and find out what that value is. All right, so it looks like it's positive. So that's what happens there. So we know that it crosses through -1.6, okay? Then it crosses through the 1, and then it just goes over to that 1.4 over there. So we kind of have a pretty decent idea to know what this one looks like. Now, what about on the right-hand side? Well, the right-hand side had no crossings. So, so what is all of this? I mean, up to here is this vertical asymptote, although I guess it doesn't really matter. And then we have to check what happens on the right of that vertical asymptote. So let me just check this. Now I have to check the other function for this. So take a test, doesn't matter. So I'll take, for instance, the number 3 and then check what happens there. And I also want to check what happens at 2 because that's where the piecewise separation is. So let's take a look if it's positive or negative right there. All right, so I'm back. Okay, so it looks like the function's negative between 2 and 6 there. And also at 2, it's -1.25. So if it's negative, then that means it's going to tend, somehow towards here. So it's going to blow up in this direction on us. And, well, we don't know what happens there, -1.25. We don't know if it goes up and then comes down or if it just goes straight down. So we kind of have to be careful a little bit there, but at least we know what's happening by the asymptote right there. And then to the right, which is over here, okay, let me just check if the function's above or below. So I'll be right back. All right, so it looks like it's above, and I did make, so if you remember, when we were doing, as our functions are approaching positive infinity, so right here, we said that this is tending towards this slant, so on the positive side. So we kind of already knew that it was going to go positive. So it definitely is above. Okay, so what that means, this is going to be tending down. Now it's going to, I guess, have a local minimum, and then it's going to go towards that slant. All right, so that's what's going to happen. So now we're pretty much have a good idea and sketch of this. So now let's see what else are we going to be doing. We found our y-axis crossing, so the next item on our agenda list, kind of nicely moving along. So we want to find the critical points, and for those critical points we have to set the derivative equal to 0. Well, this isn't going to be fun, but let me copy this. So I'm going to just take the derivative. This is just a quotient, and then I'm going to manipulate it, and then we'll see if there are, if there's any zeros here. All right, so I'm back. So it turns out actually, so here's the derivative right here. Now, I do have a problem because this doesn't have any roots. I mean, it's not a problem. It just tells me, so under the radical, so you'll notice that it's less than 0. So this does not have any roots, which means that we don't have a derivative anywhere which is equal to 0. So that's interesting, because what that is telling me that for this function, so right here, so there it doesn't go up or down or anywhere, so there's no local maximum or minimum. So we pretty much we can kind of figure out what's happening in here. So my guess now, since there's no zeros, so this just goes straight through right here, and then it just will start following that slant. So sorry, I'm running out of space there, but it will follow that slant on the left, and then there is no local max or minimums. Now, what does that mean within here? Okay, in between -3 and 2. So what that is going to be, most likely, so this is going to kind of probably cross through here, and then it's going to just take off and then go, oops, I'm sorry, just went too far there. So that's kind of my guess. Now, I mean, I can sketch it a little bit better, okay, but that's what it will be. Because we don't have any derivatives there at set is equal to 0. Now we can use the second derivative, so we can check if everything is concave up, concave down, and so on. So that will help us a little bit, but this is what we're going to be looking at. So I'm going to just remove this for the moment, and then I'll come back to this once I have my concave up and concave down, so that I'll see if there's any inflection points. But for the moment, this is all we have. Now what about the other function? So that's this one. I'm going to take the derivative here. All right, so there we have it. So it is, a little bit of work here. So here's the derivative. And so here it actually does have, 2 places where our derivative is equal to 0. So 3.76 and 3.2 something. So let me go back, 3.76. So it's going to be somewhere over here. All right, and then 8.2 something. So, okay, so it's somewhere, somewhere over here. So sorry, I mean, I guess, so it's going to happen. Now, this is actually pretty good, because now I can actually find out where that, what the y value is there. So let me actually do that. So at these points, I want to find out. So I'm going to take the point, and I'm going to substitute it back into my function to see what the y value is, so I can find the exact point to where that 0 happens. So let me do that for both of them, and then I'll be right back. All right, so here are the actual values. That was just by computing. So here's the value for y for the corresponding 3.75. So it's negative 0.47. So that's pretty good, negative 0.47. So it's going to be somewhere along here. So what that tells me, so right here, so this is great, because now, I can really figure out, okay, how this function looks like. So it's kind of like this. It has a hole, and then it will tend towards there, right? So now I am, really, really close to figuring out how this function is in terms of a sketch. Now for the other one, so for the 8.2 236, it's 8.47. So 8.47. Okay, so that's actually going to be, you know, further out here. The way that I drew it, it actually won't even. So 8.47. You know, if this was like 1, 2, 3, 4. Okay, so it's somewhere up there. Okay, I mean, I'm going to just kind of cheat a little bit. So I guess it goes like this. Okay, you know, let's assume, you know, so that basically just kind of hits that point. But that point is, you know, 8.47 or whatever it is. I mean, I scaled it down, and now it's going to kind of take off, okay, in that direction. So that's kind of how it's going to look like there. So that's already pretty good. We know that it's positive. We know that it's there. We don't really even have to check if it's concave up or concave down. I mean, we can certainly do that at these points. So we can take the second derivative and then check it for ourselves. But we already have enough information to be able to plot this. So for this function. So that is amazing. Okay, within here. So, you know, now the next thing is, you know, create test points. All right, so if we do actually create test points in here, then we definitely will know, you know, if the derivative is positive or negative, because if we get a negative derivative, we know functions like this, positive is like this. So that means, you know, we can even avoid that concave up and concave down right here. So you can certainly try and substitute your test points in there, but I'm super confident in here because I know the function's positive. I know that the slope is 0, right? So I know that it rises into the vertical asymptote, comes down. So I'm talking about to the left of 6, and then it takes off on a slant kind of just slowly and then approximates the actual slant in there. So that's, you know, as much information as we need. You can certainly take the second derivative and check it. So, okay, I can leave that with you. And in here, in this region, okay, so right, you know, for in the second region, so this region, again, I'm super confident. So we know the value, negative 1.25. We know where the slope is 0. Okay, so then it just goes up into 0, and then it just starts coming down, right? Again, vertical asymptote. It can't approach the vertical asymptote on the other side because we know the function is always negative. So once again, you can check, and we also have a hole, right, at 5. So we know that it tends towards there and it goes down. So that I don't actually need to do my second derivative for this one. I'm very confident how this function looks like here. Now on the left, the only thing really missing is between what happens between negative 3 and 2. I know that it crosses at negative 1.666 on the y. I know it crosses through x is equal to 1. But I guess I have to kind of find out where that inflection point is, because if there is no zeros, so that means it's probably going to be going concave down and then it's going to change to concave up somewhere. So there is one last item that I have to do, and I guess that's finding the inflection points, but I'm only going to do that to the function which is on the left of x is equal to 2. So that function, you know, we already have the first derivative there. So there it is. That was the first derivative. So I'm going to copy this. Let's find the second derivative. And that's going to actually complete our graph and the misery that we put ourselves through here. But it's a good worthy misery because it just really tells you if you understand all the different things that are happening. Okay, so I'm going to take the second derivative, so meaning take the derivative of this. So I'll be back. All right, so it took a little bit. I just wanted to make sure because it kind of fell apart and it looks really nice. So here's the derivative. It's very small. So that means, well, if you take a look at this, right, then you will notice that if this is the second derivative, well, we don't have any zeros. So because if we set this to 0, right, we can't find an x where this is equal to 0. So there are no zeros. That means there are no inflection points here. So that means that the derivative, the second derivative is always, well, in this case, it's going to be always concave down. okay, within that particular region. So for the X, and you can do a test point for yourself. I mean, you can just plug in the easiest test point is 0 in there, and you'll see that it's always concave down. So that's pretty neat because, so now what we know, so if I go back here, so now we pretty much have plotted the whole thing. So this is, you know, I guess I can sketch this out now, and, you know, it's going, I mean, it's a little bit trickier because the way that I have it, so it's going to look kind of like this. It's always concave down, so it's basically starts to go, this looks like a straight line, but, you know, if I, you know, scale this in, so it's, let me just draw it in here, so it's going to look, you know, from that point, okay, it's going to look kind of like that, and then it's going to approach that asymptote, right? So that's what it's going to look like, and it's always concave down. So that's pretty cool. So that's what we would see there, and then I guess on the other side, you know, to the left of -3, you can see that it's actually concave up. So we have sketched, now it's not the prettiest of sketches, but we can see how this exactly looks like. So if you were thinking about, you know, how it looks like, it basically is going to look like this, okay, then it's going to slant up that way. Then in this particular region, so it goes in, so it starts off at a point, then it goes in, then it slants down that way, so it's kind of going to look like that. Okay, over here, so it touches up somewhere over here, crosses through, and then slants down that way. So that's how they function. So these are, you know, this is my asymptote over here. It's the first one. Okay, this is my second asymptote over here. And then from here, then it basically goes like this, and then it slants out this way. So that's how the function looks like. Let me plot it on Desmos just to confirm if we have done everything necessary, okay? And again, so these 2 points, these local max and mins, you can check by taking the second derivative, but there's no need because we actually had enough information to do it. Let me pop up Desmos, let me plot these 2 on, and then to see, you know, how close were we. All right, so there you have it. Well, as you can see there, so on the left, I know it's not the nicest of spots, but we have identified all the points, right? So let's see, you know, the 0 crossings. Okay, so at -5, right? So this is what we had over there. Let's see the y. So the y was at -1.666. We found that. Let me zoom in here. Okay, the x, so that was at 1.10. We found that one. You know, how close are we in here? So notice at 2. Okay, so where did that happen? I'm going to just shift it a little bit just so you can see it. All right, so that particular 2 in there as you're going along. So you can see where it's approaching, -1 point, you know, it's going to get to 1.4. So that's what we had around there. Over here, so -1.25, that's what we got. Okay, this point, which was our local maximum, right? So -0.472 was the y value, 3.756. All right, so that's what we had. Let's see here for the derivatives. Where was it? 3.7. Okay, so we had that. So that works out great. Okay, then it blows up. And then what about this one? Okay, so within here. So we have, oh, and we had supposed to have a hole there as we go at, and basically at 5. Let's see. Yep, undefined. So we have a hole. And then the last one, there you have it. 8.236. That's the other item. So we've identified all these points. We've sketched it out, okay, within here. So that's what we have, and Desmos is showing it. So a huge amount of work, extremely long video, though I guess I, you know, was fast forwarding some of the calculations. But you can try this and play around. The steps that I use are right here to be able to see. And on purpose, I have included this, because I find that if you can do an extremely difficult example, you know, the easier examples are going to fall apart for you if you have it. Now, the reality is, you know, a teacher can't be expecting you to do this in 10 minutes. You know, I mean, you can sketch it, but not accurately sketch it. You can get a good gist of what's happening. But as you can see, if you're going to be taking derivatives, you're going to be making it more accurate. You're going to be finding the exact points that would take you a long time. All right, that is it. Okay, I'm exhausted. We'll see you in future videos in the next chapter of calculus. Bye, everybody.